Hi there. So today we're going to talk about linear versus exponential growth versus exponential decay relationships. And we're going to specifically look at word problems. So like situational application problems. When you're given a situation, how can I tell if the relationship is linear or if it's an exponential growth situation or if it's an exponential decay situation? So quick reminder, linear functions, when you graph them, they look like some kind of a straight line, as opposed to exponential functions that have this curve that kind of like flattens down here a little bit and then flattens here and then kind of like curves in the middle like that. The equation of linear functions are in the form y equals mx plus b, as opposed to the exponential functions where the x, the variable, is an exponent. But the part that I really want to focus on today is we talked about tables. So if I have a table of values, if I have like x and y values, I don't care so much about the x values, but I want to focus on the y values. If the relationship with the y value shows me an addition or subtraction type pattern, so for example, if I have like 12 and then 8 and then 4 and then 0, what's the pattern? In those y values, I'm subtracting 4 every time. So if the pattern is that I'm adding or subtracting by the same number every time, that tells me we have a linear function. And this is really going to help us out when we talk about our application problems today. When I have an exponential relationship, again, I don't care so much about the x values as long as they're consistent, but what I care about is the y values. So if I start with a number like 32, 16, 8, 4, if I look at that pattern, every time I'm dividing that previous y value by 2 to get the next number. So anytime I have the pattern of division or multiplication, that tells me that the relationship is exponential. So again, it's these two things that I'm really going to focus on to help me today. And then just quickly reviewing exponential growth versus exponential decay. Exponential growth, basically your relationship is increasing as opposed to decay where it's decreasing. All right, let's jump right in. So you're going to be given a situation and you're going to have to figure out if the relationship is linear, exponential growth, or exponential decay. So let's look. Your parents originally bought your computer for $3,000. Every year it loses value. After 1 year of owning the computer, the value of the computer is $24,000. After 2 years, it's valued at $1,920. So you really need to think about like, what are the output values, or in other words, like the y values here. So I have like years and cost. So when I think about like explanatory and response or independent and dependent variables, the year is going to be my independent or my x variable, and the cost is going to be the dependent or the y variable. So my three costs that I'm focusing on are these three numbers right here. So 3,000, 2,400, and 1,920. So I need to figure out if I can add or subtract or multiply or divide by the same number every time to get to each of the next numbers. So I'm going to tell you that you should always start with adding or subtracting. And check that. So if I go from 3,000 to 2,400, it's decreasing. So I'd be subtracting. So let's check. What is 3,000 minus 2,400? You can use your calculator, but you're going to get 600. So if this relationship is linear, I should be able to take 2,400 and subtract 1,920 and also get 600. And I can't do that because when I subtract 2,400 minus 1920, I get 480. So because these two numbers are not the same, this is not linear. So the pattern here is not subtracting. It's obviously not adding either because these numbers are decreasing. So we're going to hope that it's exponential. We're going to hope that I have a pattern of multiplying or dividing. Now this one's, I think, the harder one to check, but I'm going to teach you a trick that's always going to work. If you start with the last number and kind of work, you're going to work backwards. So I'm going to start here at the 1920. So 1920. And you're going to divide by the number, the value before it. So divided by 2,400. So 1920 divided by 2,400, use your calculator, I got 0.8. Now I'm going to take the middle number, 2,400, that I just used, and I'm going to divide by the value before that, so 3,000. So 2,400, type this into your calculator, divided by 3,000 is also 0.08. So what does this mean? It means that the relationship is exponential because, let me clean this up a little bit, but if I go back to my original values here and I multiply by 0.08, so 3,000 times 0.08 is, I'm sorry, not 0.08. My fault. Not 0.08. If I multiply by 0.8, so 3,000 times 0.8, you're going to get $2,400 or $2,400. And if I take $2,400 and multiply by 0.8 again, I'm going to get 1920. And I know that because the opposite of division is multiplication. So if I can divide kind of going backwards and get the same value, that means I can multiply going forwards and get that value. So because this works, this tells me it's exponential. And then I'm going to look and pay attention. Are these values decreasing or increasing? 3,000 to 2,400 to 1920. They're decreasing. So this is going to be exponential decay. And if I ask you why is it exponential decay, or how do you know? You're going to say because the pattern is that I can multiply the values by 0.8 every time, and these values are going down or decreasing. Okay, let's try another one. So letter B, a cable company charges $44 per month for basic service. If you have one premium channel, the total bill is $60. If you have two premium channels, the bill is $76. So the X, or independent variable, is the number of premium channels I have. I don't really care about that. I care about the dependent variable, or in other words, the cost. So my costs are $44, $60, $76. So again, like I said to you before, I would always check to see if it's linear. To me, that's kind of the easier one to check first. So if it's linear, that means there's going to be an addition or subtraction relationship. So what do I have to add to 44 to get to 60? Or in other words, you can kind of think 60 minus 44, right? So that's 16. So 44 plus 16 is 60. Can I add 16 to 60 and get 76? I sure can, and I can check that by thinking like the opposite of adding, 76 minus 60 is also 16. So because when I subtract each successive value, or when I add 16 to each value, I can say that this is linear. Okay. Letter C. On your 16th birthday, you deposit $500 into a savings account. When you turn 17, the account balance has $512.50. On your 18th birthday, it has $525.31. So I'm looking at my birthday versus the amount of money I have in the account. What is it that I'm measuring? What is it that I care about? I care about that amount of money. So that is my Y value. So it's these amounts of money that I'm going to look at. So again, check to see if this is linear first. So if I do 512.50 minus 500, I get 12.50. That's the difference there. Now, if I take 525.31 minus 512.50, the value before it, right? So 525.31 minus 512.50. Use your calculator. I get 1281. 1250, 1281. They are not the same, so it's not linear. It's not linear, so I'm going to check to see if it's exponential. And remember, my trick I told you that's always going to work. Use division. Take this last number and divide by the previous. So 525.31 divided by 512.50. You're going to use your calculator. Type that in. So I'll give you a minute. Type that in. 525.31 divided by 512.5. And I get 1.025 if I round, because it's 1.0249, right? Now I'm going to take this value that we just looked at and divide by its previous value. So 512.50 divided by 500. Type that in. So 512.50 divided by 500 is 1.025. Now this value I did have to round a little bit, and this one I did not, but they're so close. So we're going to say that they're equivalent. I mean, I get the same thing when I round. So because these two values are the same, remember that means I can think of like working backwards. So what's the opposite of division? Multiplication. In other words, if I take 500 and multiply by 1.025, I'll get 512.50. And if I take 512.50 and multiply by 1.025, I'll get 525.31. And check, use your calculator, check to make sure. So because every time the pattern is multiplying, it's exponential. And are these values increasing or decreasing? We're going from 500 to 512 to 525. They're increasing. So we're going to say that this is an example of exponential growth. Okay, so now you saw one that we looked at exponential growth, we looked at a linear relationship, and we looked at an exponential decay relationship. Now remember, in all three, I checked, was it linear first? If I rule out that it's linear, I use division over here to check to see if it's exponential. With this one, I check to see if it's linear first. If it's linear, I don't need to check to see if it's exponential. I know it's linear. And then here, remember, I check to see, does addition or subtraction work? Is it linear? Nope. So now I'm checking exponential. Okay. So here's a couple practice problems, 5 of them to be exact. So pause the video at this point. Try these on your own. First of all, you have to think about what are the values that I'm looking at, the important values. Is it years? Like for example, number 3. I have years. I have a lot of numbers here. Years. And then in red, I have attendance. What is it that I'm actually measuring? Am I measuring the year? No, the year is automatically changing. That's the independent variable, or in other words, the X. I am measuring the attendance. So I don't care about these numbers in blue. Those are the X's I don't care about. So just make sure that you're paying attention to the right numbers. All right, pause the video, take a couple minutes, see if you can work through these, and when you unpause them, we'll go over them. All right, so now that you have done some of these practice problems, let me give you some answers. So you can see here that I worked through, I showed you what I divided or what I subtracted to determine whether the relationship was exponential or linear. And then once I determined, oh, I can use division or I can use subtraction, I then said to myself, are the values increasing? So like in number 1 and in number 4, the values are increasing. So it's exponential, but it's exponential growth. In number 3, the values were decreasing, so exponential decay. I want to point out number 5 real fast. You can see that I checked first to see if it was exponential. So I took 6.7 and divided by 6.9. I got 0.97. And then 6.9 divided by 7%, that's 0.99. Those are close, but they're not close enough. Like they wouldn't round really to the same value. So it looks to me like it's not exponential. But then when I check to see if it's linear, the difference is not the same either. So I wrote none because this is not exponential, but it's also not linear. And that's okay. Not every relationship is linear or exponential. There's lots of relationships that are neither. So it's okay to say that. All right, feel free to pause here. You can check these answers, go back and check your work. But that's all I have for you. Thank you so much for watching.